The first question we have here, a guitar string is 75 centimeters long. That is the length of the guitar, which is under a string instrument. Example is a sonometer. The wavelength of its fundamental note is, we are looking for its wavelength. If you listen to the lecture well, there is a direct formula to use straight. But let me assume you cannot remember the formula. So you can quickly draw. So this is the length. So for the fundamental notes, we have something like this. So this is node, node, antinode, node. So here we have two node antinodes. So this length contains two node antinode. And we know that node antinode is quarter of the wavelength. So from here, it indicates that the length equals to wavelength over 2, wavelength equals to 2L. So this formula was given. But in case you forget, you can quickly derive by yourself. So you have to look for the wavelength. So the wavelength is simply twice the length. So the wavelength is 150 centimeters. As simple as that. For question 2, a herdsman yelling out to fellow herdsman as his voice heard his voice reflected by a clip 4 seconds later. So the echo time is 4 seconds. So this is under echo. So find what's the velocity of sound in air if the cliff is 680 meters away. So the distance is 680. Also, this is very direct. You go back to the notes. For echo, to determine the speed of sound in air using echo, the speed equals to twice the distance over t. As simple as that. So V is 2D. D is 680 over 4. Then get V to be 340 meters per second. For next thing, in a resonance tube experiment, which is illustrated, you have it here in the figure. Velocity of sound in air is 327.68 meters per second. The frequency of the tuning fork used is, we are looking for frequency. Now, for normal resonance tube, when you have the liquid, the wave enters before it's reflected, so there's always end correction. But for this particular problem, it is assumed that it has no end correction. So since there is no end correction here, so we are going to assume, it means a single length is enough. Normally, if there is end correction, 2 resonance lengths will be needed. But here we have just one resonance length, which is 16. So the resonance length here is 16 centimeters. Our aim to get velocity, and we know that V is F lambda. So we have the velocity already. To get the frequency, we need to get what? The wavelength. We should know the frequency when there is resonance. It means the frequency of the tuning fork equals to the frequency of what? Of the sound wave there. So this is the antinode, this is the node. So this is the incident wave, this is reflected. We focus on incident. So here, this length contains only one node antinode. So the length here contains just a single node antinode. So from here we can say the length equals to, node antinode is quarter of the wavelength. From here it means wavelength equals to 4N. So what's the wavelength from here? 4 times the length is 16. So therefore the wavelength is 64 centimeters. Now I want to get the frequency. This time around, we want to get a new quantity. Frequency from there equals to velocity over wavelength. So the velocity is given to be 327.68. So the velocity is in meter per second. The wavelength must be in meter. This is centimeter. So to get a meter, divide by 100. So the wavelength equals to 0.64. So divided by 0.64, that's the wavelength. From here, we get the value of the frequency to be 512 Hz. Okay, next question. All of the following are overtones of 320 Hz except, what is overtones? They are the multiples of the fundamental note. So let's assume this fundamental note. So the overtone of 320 will be 320 times 1 times 2 times 3 times 4, meaning multiples. So if we divide 960 by 320, we get 3. So this is what? Second overtone. If you divide 640 by 320, you get 2. First overtone. If you divide 320, if you divide 520 by 320, you won't get whole number, you get a decimal. So it means this C is not what? Part of the overtone, and that's the answer. 520 is not part of the overtone of 320. The quality, same as timbre, so the word timbre is also quality, of a sound depends on, based on the formula I gave. So if here, the quality depends on overtone. But in the option there's no overtone, but there's a direct connection between overtone and harmonics. So if there's no overtone, we'll go for harmonics. The answer is C. The echo of a sounder from the bottom of an ocean is at 2.5 seconds later, that's echo time, 2.5 seconds. The depth of the ocean is, recall, one of the advantage or application of echo is the determination of depth of sea. If you go back to the notes, the formula H actually equals to, let's even prove it. So from normal echo, V equals to 2H over T. Because the sound will go down, then come up. So make H the subject, H equals to VT over T. So H equals to, the velocity is we're given the velocity of, okay, sorry, you're looking for the velocity. Sorry, it's the depth. But in the question, we are given the velocity. The question is incomplete, we are given as 1,400. You can reference back to the past question. And the time is 2.5 divided by 2. That's it. From there, you can get the depth of the sea. Next, in the resonance to experiment as shown, find the speed of the sound. We know speed V is F lambda, always. So, and the frequency of the tuning fork is given, so the rate is to get the wavelength. So, and luckily there is no end correction here too. So this is node, antinode, so this is antinode rather, node, antinode, node. So that is 1, 2, 3. So the length here contains 3 node antinode. The length is given to 0.3 meter. 3 node antinode is what? Lambda divided by 4. So from here, if you multiply 3 lambda equals to, multiply this one, 1.2. Also by 3, we get the wavelength to be equals to 0.4. Then we cannot get the velocity, V, which is F lambda. So the frequency is 760, and the wavelength is 0.4, and our final answer is 304 meters per second. Now, next question 1983, let me read the question. Please listen to the question. The question goes thus. In a resonance tube experiment, a tube is fixed, or fixed length rather. In a resonance tube experiment, a tube of fixed length is closed at one end, and several tuning forks of increasing frequency used to obtain resonance at the open end. If the tuning fork with the lowest frequency, which gives resonance, has a frequency of F1, and the next tuning fork gives a frequency or give resonance at a frequency of F2. So this is the first one, followed by this. So the question says the ratio of F2 to F1 is F2 to F1 is that's what we are looking for. And recall, for a resonance tube is like a closed pipe. And recall, for a closed pipe, what's the pattern? If the fundamental is F naught, the first overtone is 3 F naught, then followed by 5 F naught and the likes. So it means our F2 is 3 F naught, our F1 is F naught. So the answer is 3 F naught over F naught, and the answer is what? 3:1. We just say 3. The next one is also under echo. A ship traveling towards it will receive echo 3.5 seconds, so the echo time is 3.5 seconds. After the 3.5 seconds, a short while later, the ship's approaching the cliff. So as the ship is moving closer to the cliff, the distance decreases. So the echo time will also what? Decrease. Then it receives another echo time of 2.5. So let's say this is the first echo time, T1. Then the second echo time is what? 3.5. So what's the question? How much closer is the ship to the cliff? So suppose the distance of the ship from the cliff initially is D1. Now it is closer, it is D2. So how much closer? We are looking for the difference between D1 and D2. So that's changing distance. D1 is actually greater because the ship is moving closer. So we are looking for D1 minus D2. So our aim is for us to get the value of D1 and D2. So if the speed of the sound is 250 meters per second, so we know that V is 2D over T. We make D the subject, it means D equals to Vt over 2. So for D1, it's going to be Vt1 over 2. What's V? 250. T1 is 3.5 over 2. We are going to do the same for D2. For D2, that will be Vt2. That's V. Then T2 is 2.5 over 2. And then from here, if you calculate this, you get the value of D1. From here also, you get the value of D2. Then we subtract the answer. So D1 is 437.5 meters and D2 is 312.5. So what we want to get is the difference. And if you subtract, you get 125 meters. So it means the sheet is 125 meters closer, and that is why the echo time decreases from 3.5 to 2.5. Of two identical tuning forks, meaning they both have the same frequency, which natural frequency 250 Hz. So the first one 250 Hz, 256 Hz, then called F1. The second one is also 256 Hz. One is loaded. So when you load a tuning fork, maybe by adding a mass weight, the frequency will drop. So let's suppose this first one was loaded. So frequency will drop from 256 to something that is less. Let's call it X. But we know this X is less than this. One is loaded so that 4 beats per second are had. 4 beats per second. If you recall, I said the frequency of the beat is different between the frequency of the two sources. So here, what will be different? That will be this minus this. Because it's actually what's smaller. So we are going to remove this one from this. So the frequency of the beat will be 256 minus X. And we are told that it is what? 4 beats per second. So that's 4 equals to 256 minus X. From there it means X equals to 256 minus 4. S equals to 252 Hz. So the tuning fork that was loaded will have a frequency of 252 Hz, while the second one is 256 Hz. So the difference gives us what? 4. Next one. If the fundamental frequency of a closed organ pipe a day, when the speed of the sound is 340 meters per second, is 170 Hz. The length of the organ pipe is, so from here what can we get? We can get the wavelength straight, since V is F lambda. Then wavelength lambda equals to V over F. So the wavelength equals to 340 over 170. From there, we get the value of the wavelength to be 2 meters. Now, for organ pipe, if you look, the connection or the relation between lambda and the length is lambda equals to 4N. You can check it out. Go and check the notes. Check your notes. That's why you have to take notes during every lecture. So this time around, the wavelength is 2. We are then for the length. From where the length equals to 2 over 4. So the length is 0.5 meter long. Next, a wave of frequency 10 Hz forms a stationary wave pattern in a medium where the velocity is 20 centimeters per second. The distance between adjacent nodes is, we are looking for node distance. And if we check the nodes for stationary wave, distance between two successive nodes or two successive antinodes is half of the wavelength, lambda over 2. Node, lambda over 2. Antinode, lambda over 2. Node, antinode, lambda over 4. Crest, lambda, that's wavelength. Trough, wavelength. So to get the node distance, we need to get the wavelength first. How can we get wavelength from here? V is F lambda. So we can get lambda to be V over F. So the wavelength equals to, the velocity is 20 centimeters per second, and the frequency is 10 per second. Because the hertz actually means per second. I'm just trying to demonstrate here that we don't need to convert, since per seconds will cancel per second. So it means the wavelength is what? 2 centimeters. Our aim is to get the node. So the node distance is what? Wavelength over 2, and wavelength is 2 over 2. So the node distance is 1 centimeter, and that is the answer. Next question. The lowest note emitted by a stretched string has a frequency of 40 Hz. So this 40 Hz is what? The fundamental note. Then I ask, how many overtones are there between 40 and 150? We know for a stretched string, the pattern is F0, 2F0, 3F0, 4F0, and the likes. So it follows natural number. So if you are to write, this is our fundamental 40 Hz. Second one will be times 2, 80 Hz. Times 3, 120 Hz. Times 4, 150 Hz. Times 5. But it said between this and this. So how many overtones do we have? This is the fundamental. So this is the first overtone, second overtone, and this is third overtone. So, but the thing is, if they say between 40 Hz and 150 Hz, is 150 Hz inclusive? If 150 Hz is inclusive, then the answer is 3. We have 3 overtones, first, second, and third. So we have 3 overtones between 40 Hz and 150 Hz. A piano wire 0.5 meter long, so we are given the length of the piano to be 0.5 meter, has a total mass of 0.01 kg. But what we actually need is mass per unit length, not ordinary mass. So the mass is 0.01, the wire is 0.5, so it means the mass per unit length is 0.02 kilogram per meter. Is stretched to a tension of 800 Newton. So the tension is 800 Newton. Calculate the frequency of the wire when it sounds its fundamental note. So I think for the fundamental frequency. So for a stretched wire or string, so the fundamental note is 1 over 2L root T over mu. We've done this. So check the lecture. So that's for the fundamental note, which is 1 divided by twice the length, 0.5. Square root of the tension is 800 divided by 0.02. So if we solve this, you get a final answer. Let's continue. 2 times 0.5 is 1, that will be 1 over 1. Roots, here 2 zeros, that's 80000 over 2. So the frequency becomes root 40000. So the frequency is 200. Then 200 Hz. 2 strings of the same length, it means length is constant. Under the same tension is constant. Gives note of frequency 4:1. So you can say the frequency of the first one to the second one is 4 over 1. The masses of the string are a ratio of the length for m1 over m2. Or better still, mu1 over mu2. Because the length will be the same and the length will cancel out. So the equation is still connected to this. So in this question, the length is constant, tension is constant. So we are relating frequency to the mass per unit length. And what's the relation? The frequency is inverse proportional to the square root of mass per unit length. From here it means frequency equals to k over root mass per unit length. Then from here it means the constant is frequency times this. So we can say F1 root mu1 equals to F2 root mu2. Since our aim to get mu1 or mu2, we can square both sides. If we square both sides, we are having F1 squared mu1 equals to F2 squared mu2. This is just variation. So to get mu1 over mu2, so from there, mu1 over mu2 becomes F2 squared over F1 squared. In short, mu1 over mu2 equals to F2 divided by F1 all squared. So mu1 over mu2 becomes F1 or F2 is what? 4 over 1. 4 over 1 all squared. So the final answer is 16 over 1. 16:1. So mass per mass, mass per unit length, the length cancels each other. Oh, there's a mistake here. So we are given F1 over F2, not F2 over F1. What we need is F2 over F1. So take the reciprocal of this. So if F1 over F2 is 4 over 1, it means F2 over F1 is 1 over 4. So what I'm going to put here is going to be 1 over 4, not 4 over 1. 1 over 4. And the final answer is 1:16. Please always note this kind of error. Next, when the tension in a sonometer is doubled, the velocity will, what happens to velocity if the tension is doubled? Recall for a sonometer, the velocity is proportional towards square root of the tension. I explained that in the lecture. So where V equals to K root T, K equals to V over root T. From here it means V1 over root T1 equals to V2 over root T2. I'll aim to get the new velocity V2. If you make V2 dissolve from here, V2 equals to V1 or root T2 over T1. Try to make V2 the subject together. So we are told that the tension is doubled. So it means if the original tension is T, the new tension is what? 2T. So velocity equals to V1 root T2 is 2T over T. So T cancel T, so it means V2 equals to V1 root 2. So when the tension is doubled, the velocity will increase by a factor of root 2. So the new velocity will what? The initial velocity multiplied by root 2. Here you might be wondering that we are told to look for the ratio of the masses, not mass per unit length, but they are equivalent. We can show that mathematically. So mu1 can be written as m1 over L, mass per unit length, divided by mu2 is what? M2 over L. Since the length is fixed, that's m1 over L times L over m2. Cancel, m1 over m2. So meaning if you divide mu1 by mu2, you still get m1 over m2 because the length will cancel out. Okay, what is the frequency of the sound made by a siren having disc with 32 O's and making 25 revolutions per second? So let's suppose this is siren and it has O's. So if this thing is revolved, the more the revolution, the more the frequency. So the formula is actually the frequency is number of revolution per time of revolution times the number of O's. So if you have just a single hole, then this is 1. That will just be number of revolution times time. But here we have what? 32 O's. And luckily we are already given revolution per second. So number of revolution per second is given to 25. So the frequency directly is 25 times number of O, 32. Frequency is 800 Hz. As simple as that. The note produced by a stretch string has a fundamental frequency of 400 Hz. So the fundamental note is 400 Hz. If the length of the string is doubled, so let's put the original length L1 is L. The new length is what? 2L. If the length is doubled, why the tension is increased by a factor of 4? So it means if the original tension is T, the new tension T2 is what? 40. The frequency will still be 400. Why? Because the effect of the length and tension will cancel each other. How? Okay, let's show it mathematically. So we know that the frequency F for a string is, for fundamental, is 1 over 2L root T over mu. So we are told, so in this case we are going to assume the mass per unit length is constant. So we are relating tension length. So what happens? Let's get the new frequency. Let's call it F1 this time around. Or let's call this one F1, F2. For F2, I'll write 1 over this L1. 1 over 2 L2 square root of this T1. What's our T2? 40. That's just T2 over mu. So if you have to divide this together, if you have to do, let's say, F1 over F2. What happened? These two cancel these two here. So here I have L1 is L, so I have 1 over L up. And L2 is what? L2 is 2L. 2L. Then square root of this and this, they are equal to cancel out. T1 is T. T2 is 40. So if you simplify this one, F1 over F2 becomes, so what happened here is this L here will cancel this L because this one will go up to cancel each other. So this L here cancel each other. So 1 over half is 2. So if you do 1 over 1 over 2, that's 2. Then from here, this cancels this. I'll have square root of 1 over 4. If it's confusing, do it by yourself the way you understand. That's 2 times root 1 is 1, root 4 is 2. So that's what 2 over 2. So F1 over F2 is what 1 over 1. You can multiply, it means F1 equals F2. So since F1 is 400, F2 is still 400. So the frequency remains unchanged. I didn't mean the length was increased and the tension is left. Yes, it will change. Well, the effect of the increment in tension and the length cancel out each other. Why? Because frequency to length is inverse, to tension is what? Direct. And because of this square root, that's why square root of 4 is 2. That's why I calculated that it's going to cancel out. So the answer is what? It's still 400 Hz. So since F1 equals F2, so it means F2, the new frequency is 400 Hz. Number next, under constant tension and constant mass finite length, the note produced by a plugged string is 500 when the length is this. In this case, they are still under what? String. Same formula. F equals to 1 over 2L root T over mu. So we know that the frequency and length, they are inverse proportional from here. So tension and mass per liter is constant. So what we are using is frequency proportional to 1 over L. Frequency equals to K over L. K equals to FL. It means F1 L1 equals to F2 L2. Our aim is to get the what? The second length. At what length is the frequency of that? So our L2 becomes F1 L1 over F2. So our L2 becomes, what is F1? First frequency is 500 Hz. L1 0.09. L2 150. By the time you press calculator, you get the final answer to be 0.3 meters. So something about physics is one of those topics you need to master in physics. To know physics, sorry. One of the topics you have to master in mathematics in order not to have issue in physics is variation. As we are here, we use variation, all this while. So how do we get this relation? It is from the formula, as you can see. Frequency length, it means they are inversely. Frequency tension, proportional to square root of tension. Frequency mass per unit length, inverse proportional to square root of mass per unit length. So it means from this formula, L equals to 1 over 2L root tension over mu. If these two are kept constant, it means frequency to pick up to tension is related this way. If tension is fixed and this one is fixed, it means frequency and length, they are inverse related this way. If the length and tension is fixed, it means frequency and mass per unit length are related this way. So depending on what is constant, will determine what you pick. And we've used this one to solve the question today, and this one we've used the three relation. Next, the velocity of sound wave at 27 degrees Celsius is 360. So let's say V1 is 360, when temperature T1 is 27 degrees. Oh, then I have to convert to Kelvin. Recall, the first thing I said when we started the lecture, sound wave, there are factors that affect the speed of sound. One of it is increase in temperature, and the temperature must be absolute, must be in Kelvin. So that's 300 Kelvin. So then I ask, its velocity, you are looking for V2, its velocity at what? 127 degrees is, it means T2 is 127, you have to add what? 273. So from here it means T2 equals to 400 Kelvin. So what is the non-relation? The relation is that the velocity of sound is proportional to the square root of the absolute temperature. During the lecture, I use theta, but just a symbol. And from here, it means K equals to V over root T. So it means V1 over root T1. Another thing, relation again, V2 over root T2. So what do you need? We are looking for V2. From here, V2 equals to V1 root T2 over T1. So V2 becomes, what's V1? 360. What's T2? 400 over 300. So that will be 3 root 3. Let's just do it without calculating. So 2 zeros here, cancel these 2 zeros. So this becomes 360. Root 4 is 2. Then 3 is not over square root 3. So we can rationalize by multiplying by root 3 over root 3. Root 3 over root 3. So root 3 times root 3 is 3. So 3 in 360 is 120. 120 times 2 is 240. With this root 3 here. So the answer should be 240 root 3 meter per second. To get the answer in decimal, you can just press calculator. The answer in decimal will be 5.6 something. So, but the answer in the options is in short form. So, another thing is we use sword here also. You have to know sword. The first question here: find the frequency of the first 3 harmonics of a piano string length 1.5 meters. If the velocity of the wave in the string is 120 meters, so the velocity is equal to 120 meters, and we know the pattern for a stretched string is fundamental notes, first overtone, second overtone, and the likes. So we only need to get the fundamental notes. So, and what are the fundamental notes for a stretched string? If you can recall from the diagram, so this is it. Node, antinode, node. So here we have 1, 2. So the length here contains 2 node antinode. That's 2 times lambda over 4. So our aim to be able to get the frequency, we need to know the wavelength. From here, the wavelength equals to 2L. Similar to the first question we solved rather. So the lambda is twice the length, and the length is 1.5. So the wavelength is 3 meters. Velocity is frequency times wavelength. Frequency from here equals to velocity divided by wavelength. Then the frequency is, the speed is 120, wavelength is 3, so it is what? 40 hertz. But we are looking for the frequency of the first 3 harmonics. So when we talk about harmonics, just multiply by the factor. So meaning you are going to have 40 hertz, and the fundamental, then times 2, 80 hertz. 4 times 3, 120 hertz. You have to continue, 150 hertz, and the likes. So the first 3 harmonics are this. This should be 160. The first 3 harmonics, 40 to 120. Next, a string is fastened tightly between 2 walls, 24 centimeters apart. That's the length. The wavelength of the second overtone, let's say this is the one. So this is fundamental note. This will be first overtone. But for the second overtone, we have something like this. If you check the notes, it's there. Or the previous lectures. So node antinode 1, 2, 3, 4, 5, 6. So the length here, L, contains 6 node antinode, and node antinode is lambda over 4. So our aim is to get the wavelength from here. L equals to 3 lambda over 2, and the wavelength is 2L over 3. Is in your note to be checked. So that is 2. The length is 24 divided by 3. 3 in 24 is 8. Then 8 times 2 is 16. So it means the wavelength is 16 centimeters. For the next question, a tuning fork of frequency 340 Hz is vibrated just above a cylindrical tube of height 1.2. So the total length of the tube L is 1.2 meters. If water is poured slowly into the tube, at what maximum height will resonance occur? I think they've simplified it by asking at what maximum height. So at the maximum height, the frequency at that moment is going to be the what? Fundamental note. Let me just draw a diagram. Suppose this is the tube. When water is at this level, there will be, let's say, resonance. As we pour more another level, there will be resonance. Another level, there will be resonance. Another level, there will be resonance. So the highest resonance, or the highest height that will give resonance is what? The fundamental note. Fundamental note, the length here is what you are looking for. Let's call it L. This antinode node. So the length contains only one single antinode. So this length, this particular length is this. It contains one antinode, which is lambda over 4. So you need to get what? The length. So what is the wavelength? So V, we are given the velocity, we should be given the velocity 3,000. We should be given the velocity because ordinarily V is F lambda. So our aim is to get lambda first. So lambda becomes V over F. So let me check the question if the velocity is given. Yes, the velocity is given as 340 in the question. So the wavelength becomes velocity is given as 340. The frequency is also 340. So the wavelength is 1 meter. So we come here, the length L equals to wavelength is 1 over 4. So the length is 0.25 meters. That's the length from here to here. The length of the air column that gives that 340 frequency, which is the fundamental note, is that. But what's the question? They ask, at what maximum height will the resonance occur? So this is the length of the air column, but what's the maximum height from here to the ground? From here to the ground is what we are looking for, maximum height. Is what we are looking for. But we are told that the total length of the tube is 1.2. So from here to here is 1.2. The one up here is what? 0.25. So our H will be total length, let me write as LT. Total length is 1.2. Minus 1 at the top here, 0.25. And the height should be 0.95, I guess, meters. Okay, next question. Given that Young modulus for aluminium is 7 times 10 to the power 10, I know where this is going already, and density of aluminium is 2.7 times 10 to the power 3 kilogram per meter cube, find the speed of sound produced if the solid bar, let's say the solid aluminum bar, is struck at one end. In short, we are looking for the speed of sound through aluminium. And recall, first thing, when we began the lecture, factors affecting the speed of sound, number 1 is the Young modulus, or the elasticity of the medium, and its relation. And for the density, it is inverse proportional to the square of density. And I remember that we showed that the velocity equals to root this over this, 0 naught. So we are given the Young modulus and we are given the density, just impute the value and get the final answer. So our V here becomes square root of the Young modulus, that's 7. 7 times 10 to the power 10. 7 times 10 to the power 10 divided by the density, 2.7 times 10 to the power 3. So you press the calculator, you get the velocity of sound through aluminum solid bar as 5091.75 meters per second. This will be the last question. If the distance from a point source of sound is doubled, by what factor does the intensity decreases? Recall during the course of lecture. So I think when I was explaining the intensity as a factor that affects the as one of the characteristics of musical notes. So I said in there that intensity is inversely proportional to the square of the distance between the point source and the observer or listener. So in this case, I equals to K over this. K is IB squared. So it means I1 D1 squared equals to I2 D2 squared. We are left for the I2, and I2 is I1 D1 over D2 all squared. The distance is increased by 2, so it means if the initial distance is D, the new distance is 2D. So in this case, it means I2 equals to I1 into D over 2D all squared. So from here, it means I2 equals to I1 into 1 over 2 all squared. Then I2 equals to I1 times 1 over 4. I2 equals to 0.25 I1. So the new intensity is 0.2 times what? The original intensity. So this is decreased because this is a proper fraction. When we multiply a proper fraction by a number, it gets smaller. So that's why there is the word decrease. It decreased by a factor of 0.25 or a fraction by a factor of 1 over 4.